Suppose we have two homogeneous charged spheres, and in this thought experiment we are overlapping one sphere which is negative charged with the other sphere which is positively charged. And then of course for every negative charge in this region there is a positive charge. So this region is neutral. And we realize if you completely overlap those two spheres, then everything is neutral and the electric field everywhere must be zero, inside and outside. But for the problem here, there is a distance d between the centers. And the charge density is rho, and here negative rho, or if you like the total charge of that sphere, negative q total, and q total here. So we are supposed to compute the electric field inside the overlapping region here. And what we can do is using the superposition principle. So inside that sphere there is an electric field at a certain distance from its center, and so let's calculate that, and the same goes for the other sphere. So let's calculate that for the same point wherever that is, and then we sum both contributions. So that's the superposition principle, that you can sum electric fields. So let's first find out what is the electric field inside a homogeneous sphere. And Gauss theorem for the electric flux shows that if you're standing here at a certain distance r, then only the charge beneath you, so to say, matters, and everything above you are spherical shells, and a spherical shell gives a zero electric field. So that shell, for example, if you're anywhere, then the electric field is zero, and then the next shell and the next and the next, all of them contribute nothing. So the only contribution is the charge beneath here, or the sum of the shells beneath, and that is just the charge and then Coulomb's law. So what is the charge beneath you? Yeah, so it's the same density everywhere, so also here it's density rho. And what is that volume for a sphere? Yeah, it's this one. And we can also take the whole sphere. Yeah, that's the q total I'm mentioning here. So that's rho times the volume of the whole sphere. So we can relate the partial charge in that sphere with the total here. And you see, if you divide this by this, then you get this. And now you can calculate the electric field from the positively charged sphere at a certain distance from the center, r plus. So if we call that r here, for example, r plus. And according to Coulomb's law is 4 pi e naught, and then the r squared. The r plus we call it here. And but this q r plus, if you multiply with q tot, then you get this instead. A little simpler expression. And r plus, yeah, there are r cubed here, so that will be r plus divided by capital R cubed. And the direction of electric field here is outwards because it's positively charged. Then the electric field is outwards. So I call that unit vector here ER plus, indicating it's for a plus sphere here. And then we do the same calculation for the negative charge sphere. but now it's from this center and a certain distance, r minus. So you get this. And then we notice from this figure here, this field here is in the r plus direction, this direction. And here we have unit vector r minus, it's this one. And a negative charged sphere, it has the electric field not outwards, but the opposite direction to this. So that's why you have the negative sign here. And note that this unit vector is the negative of that one. So then if you introduce that vector, then you have a minus here and a minus here. So they cancel out. So it's this one. The same now is the same direction here. ER plus. So then we can sum E plus plus E minus. So let's do that, and then you get this result here. Okay, so what is R plus plus R minus really? So let's look at the overlapping sphere here. We were given that the distance between the centers are d. And here, let's consider one point here where we would like to know the electric field. So then there is a certain distance r plus to that point. And from the other sphere, it's a certain distance r minus, a smaller distance, right? And then you see this distance r plus this distance. Yeah, that's just d, isn't it? And fortunately, this is exactly the expression we have here. So you can just put in the number d here. So then you get the final result, and it can be simplified to this if you like, but it doesn't matter if you write it like this or like this. It's exactly the same thing. And note here that it's actually in agreement with what I said before, that if the distance d equals 0, so those two spheres are overlapping completely, then of course for every positive charge here, there is a negative charge here. So the whole system will be neutral, and the electric field must be 0, not only inside, but also outside. Anyway, if d equals 0, yeah, the electric field is 0. So thank you very much for listening, and like, subscribe if this was helping you.